All right, so today we're going to talk about mechanical energy, which we actually technically talked about in last time, but this is just complicated, more complicated, we'll say. So, starting off with, let's say that I have this swing here, and let's say the swing, the seat of the swing sits. Oh, let's say it sits half a meter off the ground, and we'll say that the swing itself. The chain of the swing is 3 meters from the seat all the way up to where it, pivots back and forth. And let's say somebody's swinging really, really vigorously, and they're able to get the swing to where it's kind of perpendicular with the frame and stuff. Okay. So then the question is, I would ask, how much gravitational potential energy does the swing have? And let's say like there's a person on it with a mass of, that's going to be my person, they're a potato person, with a mass of 50 kilograms. So they're a kid. All right. So figure out the GP, so the total height. So typically the swing, we know that the frame of the swing, the top of the rope there, is 3.5 meters off the ground, and if the person is perpendicular to it, they're 3.5 meters off the ground. And they got a mass of 50 kilograms. So the GPE up the top part of the swing here, let's draw my person on it, okay, is equal to the mass times acceleration due to gravity times height. So in this case, that's 50 kilograms times 9.81 meters per second squared times the height, which we said was 3.5 meters. All right, so calculator out. Bring this over. Should probably make that shorter. There we go. All right, so 50 times 9.81 times 3.5. All right, 1,706. We'll round up. So 1,717 joules of gravitational potential energy at the top of the swing. Okay. So the person down here at the bottom, they swing upward, the swing goes up, and then we know from experience that swing's going to swing back down. So we still have energy changing form. So at first the person, maybe there's somebody pushing them, maybe they're pumping, pumping the swing themselves. They're adding work into the swing. That work is a transform of energy that becomes kinetic energy, that becomes gravitational potential energy. For the swing, so let's say that the big question we want to know is at the bottom, what's the kinetic energy at the bottom? Because we want to know how fast is that swing going at the bottom of the swing. All right, so we've got our gravitational potential energy here. Now, where this differs from the transforming energy video, those problems, is this swing isn't coming down to the ground. The swing's only coming 0.5 meters away from the ground. So in order to figure out our kinetic energy, we're going to need to figure out what our change in GPE is, because whatever our difference in gravitational potential energy from the top of the swing to the bottom of the swing, in this case, that change in gravitational potential energy will equal the amount of kinetic energy gained by the swing at the bottom. All right, just to kind of let you know where we're going here. So let's figure out the GPE at this point. I'm not going to rewrite the equation out, it's just mgh. So we've got 50 kilograms. We're still on Earth, so 9.81. But in this case, my height is going to be 0.5 meters, okay? So this time, bring the calculator back over. There we go. So we've got 50 times 9.81 times 0.5. 245 joules is what I'm going to round that down to. So down here at the bottom, the swing, the pendulum, whatever it is you want to call it, still has some gravitational potential energy. It has 245 joules of GPE. Essentially, that's how much energy, like if the person just sitting down on the swing, they would have that much GPE. And somebody could cut the rope and the person would fall. and then they'd hit the ground, with that much kinetic energy. Thank you. So with that, so now we can figure out our change in GPE. That's going to be equal to 1,717 minus 245. So our change in GPE, and I don't feel like doing that in my head today. 1717 minus 245. 1,472 joules. All right. 1,472 joules. All right. So that's how much KE we're going to have as well, right? Because we know as I'm swinging, my gravitational potential energy becomes kinetic energy, just not all of it. In this case, it's just most of it. So I'm just going to do that messily like that. Keep in mind, so we answered one part. The kinetic energy is 1,472 joules. So now I can use kinetic energy is equal to 1/2 mv squared. If I want to know how fast the person is going on the swing, I just solve for v. So v squared is equal to kinetic energy all over 1/2 mass, square root both sides. V is equal to the square root of kinetic energy over 1/2 m. So in this case, let's plug in some numbers. So I've got 1,472 joules over 0.5 times 50 kilograms. All right, so let's see how badly I mess up typing this in. Let's go that. Square root of 1. Nope, that's not going to work. Okay, so let's just go like this. 1,472 divided by 0.5 times 50, close parentheses, square root. All right, that looks like what I wanted it to do. So the answer is 7.7 is what I'm going to call that. So at the bottom of the swing, this individual is going 7.7 meters per second. That's pretty fast. This person's booking it on this swing. All right, so that's kind of energy. It's energy transformations when we're not really converting all of our energy. So bringing this to mechanical energy, really what we're going to find is mechanical energy is the sum of all of the energies of an object. So we would be adding their kinetic energy plus their gravitational potential energy plus their elastic potential energy, and if we wanted to throw in a little bit of chemistry, even their chemical potential energy. Really, mechanical energy is just the sum of all these things, and it's just kind of saying your mechanical energy just doesn't, it's never zero, for a certain event, if you will. So in this case, let's look at the practice problem I have down there at the bottom, right? So I'm going to do this kind of the laid out way, the not standard, but I'm just going to be organized about this. All right, so 0.13 kilogram ball. So right away, they're giving me a mass of 0.13 kilograms. It's placed on a vertical spring with a spring constant, that'd be K, of 1,000 newtons per meter, and compresses it 0.1 meters. All right, so I have an X, 0.1 meters. They want to know how fast the ball would be going, so I'm looking for a velocity halfway through its flight. All right, so essentially, so I've got a ball, push it on a spring. Okay, we push it down, and then once that spring is released, we know that the ball is going to fly up, and the ball is going to stop, and then the ball is going to come back down. So really what we see is we have elastic potential energy that becomes kinetic energy and then that kinetic energy becomes gravitational potential energy. Like, that's the energy transformations taking place here. And then we'd have the reverse coming on, you know, if it fell straight back down and compressed the spring again. So really here, the two things I'm looking at here is, ideally, my potential energy, all of my elastic potential energy, should become gravitational potential energy. Like, it should all become kinetic energy right away, which becomes GPE. So I should probably start by finding the elastic potential energy. So the equation we're going to use for that is 1/2 spring constant times its distance stretched or compressed squared. So in this case, 0.5. Spring constant we said was 1,000 newtons per meter. That's a pretty stiff spring. And we need to square the distance, which is 0.1 meters squared. All right, so in this case, let's bring this back over. All right, so 0.1 squared times 1,000 times 0.5. So 5 joules. 5 joules is stored elastic potential energy. So the question then says halfway through its flight. So halfway through its flight, so right away we have the potential, the elastic potential energy. Immediately when it leaves the spring, all of that PE elastic has become kinetic energy. Halfway through its flight, what we're going to find, let's even call this kinetic energy at the halfway point. Halfway through the flight, half of our kinetic energy should have become gravitational potential energy. So halfway through its flight, half of this 5 has become GPE. So really we just have 5 joules divided by 2 is equal to 2.5 joules. All right, so the one way to kind of think this one through is halfway through the flight, half of it's been transformed, we're left with 2.5 joules. So now I can go back through and I can use KE equals 1/2 mv squared. Or if I wanted to cheat a little bit, I know that V is equal to the square root of kinetic energy over 1/2 m. V is equal to the square root kinetic energy over 1/2 mass. All right, so in this case, 2.5 joules over 0.5 times the mass. We said it was 0.13 kilograms. All right, so back over this way. Let's go there. Just because I know this way worked with this calculator. 0.5 times 0.13 square root 6.2. So that ball is going 6.2 meters per second. Halfway through its flight. Right away, it would have been going much faster, but we can kind of think that through. Gravity starts accelerating it downward. You know, we're losing kinetic energy to GPE. Really, it's just finding what's your change in energy, and just kind of keeping in mind. I'm going to ignore the physicsy or the chemistry part there. The mechanical energy for a system just doesn't change. So whatever the mechanical energy is here, you know, when the spring is compressed, 100% of our mechanical energy was elastic potential energy. As soon as that spring's released, 100% of our mechanical energy was kinetic energy. And then as it went up, that kinetic energy became GPE at the top of the flight, I guess, when 100% of the mechanical energy was GPE, and then it's always some proportion of that on its way down of GPE and KE. I think I've babbled enough for this one. Hopefully that sheds a little bit more light on it. On the fact that, you know, mechanical energy typically for an event just does not change. Good luck with the practice problems.